This paper presents a fast and practical method for simulating the sound of non-empty objects that contain a fluid. Sound is integral to the level of immersion and sense of presence in virtual and imaginative environments. Game engines and VR systems are incorporating physically based graphics and sound simulation algorithms for interactive and realistic effects to help users remain immersed in the experience. One of our contributions is adding new preprocessing steps to the rigid body sound pipeline before performing modal analysis. As a result, this can be completed before simulation, allowing for usage in real-time interactive systems. The first step is to identify mesh nodes of the structural object bounding the liquid. This includes boundary nodes as well as adjacent domain nodes. Second, we modify the elements of the mass matrix M for these identified nodes of the structural object by an amount proportional to the liquid's density or force along the fluid structure boundary. After completing these two steps, continue with the existing pipeline. Our algorithm is based on the principle that the accelerating or decelerating structural vibration must move the liquid along with the structure. This is known as an added mass operator or added mass effect, where the weight of a surrounding liquid can be added to the system by modifying the mass matrix of the structural object at boundary and adjacent nodes by an amount proportional to the contained liquid's density and volume. Note that mass added to the mass matrix is included in the damping matrix as well, assuming that we are using the Rayleigh damping model. Randomly distributing the added mass over the entire structure also modifies the sound, but the resulting frequencies are closest to real-world recordings when we distribute the added mass uniformly or weighted based on the local force along the fluid structure boundary. In the next two videos, we compare the results of a real water xylophone to the one simulated by our algorithm based on varying amounts of liquid contained by each glass. The following two videos demonstrate how our approach generalizes to different impermeable solid objects and inviscid liquids that are at rest in hydrostatic equilibrium in a non-moving domain. Now let's review the results of our interactive technique applied to different objects containing varying amounts and types of liquid in a virtual environment. Next, we demonstrate a user interactively playing an octave and demo song with a simulated liquid xylophone containing various objects and liquids. In summary, our sound synthesis for fluid structure coupling algorithm contributes in three primary ways. 1. It transforms an object containing a liquid into a single fluid structure system using the added mass operator. 2. It enhances the rigid body sound synthesis pipeline with preprocessing steps for objects containing a liquid. And last but not least, it may be applied to real-time interactive virtual reality applications.